All right, this is a continuation of non-homogeneous second order linear differential equations and solving for particular solutions. One more final example of kind of a special case that might happen to you in this method. So one thing, I know in the problem it says to only do the particular solution, but we need to look at the complementary function here, or the complementary solution. So if I look at the auxiliary equation for the left-hand side, I get two factors. And so my complementary function, let's see, m equals 1 and m equals 4. And this would be good for that left-hand side. What I need for you to recognize, though, is if I let my particular solution just model the right-hand side, I don't have linearly independent solutions here. So instead, we're going to just put an x in the front. Now these are linearly independent solutions, and let's just see what happens when we plug in. Okay, derivative first, second, first derivative of second. Okay, so now let's plug this into the left-hand side and see what happens. So 2a e to the x plus ax e to the x minus 5 of yp prime plus 4 of yp. Okay, now when I go to try to look at this front part with the x e to the x, I should have an a in the front there. Notice these all cancel out. There is no x e to the x term here, which makes sense. So I'm good to go there. They all go away when I plug in. And so therefore I need -3. I'm getting -3 from to be equal to the right-hand side. So a must be -8/3. And so my particular solution is -8/3 x e to the x. And so if you have a time where your particular solution would be a repeat of something in your complementary function, this is kind of the trick to figure out where you would need to start so that you can have a linearly independent solution. And then notice, even though I have an extra x in there, when I do take the derivatives and plug them in, right, those things, oops, I kind of circled wrong because those things went away, right? So we're left with the ability to solve this for the particular solution in this form.